Engineering department I am working, and I am going to teach you the design of structures, and the subject code is 3150612. The subject R&B third year SEM 5th. So in this lecture we are going to learn unit 2, which name is Philosophy of Limit State Design for the RC Structures. So shall we start? First tiles is for the content. In this chapter we are learn the limit state of collapse, limit state of serviceability. In serviceability we have three types of method. There is limit state of deflection, limit state of cracking, and other limit state. Then after partial safety factor, and last one is neutral axis. In neutral axis we are going to find two examples of the find neutral axis. So first of all we start limit state of collapse. So topic is here, it is a limit on achievement of which the structure is likely to collapse. A design to this limit state ensure safety of structure from collapse. Means in the limit state of collapse we ensure we achieve a structure whenever we collapse. Limit on achievement of which the structure is likely to collapse means if in the design by a limit state of collapse we assume our load that much higher, then your structure will be collapse. In collapse condition we get safety. Understood? The simple logic is here. For the limit state of collapse we assume a structure load that much higher that the structure will be collapsed. Okay, and by this method we ensure safety of the structure. Okay, and there are following two types of collapse. We have collapse of one or more member occurring as a resultant force coming on the member exceeding its strength. Means the material strength is not much that level that your force will be applied on the structure. Okay, that time your structure will be failed. Then the second one is displacement. Displacement we also have called a failure. Then after various conditions here to leading a structural failure is followed. First condition is breakage. In the breakage we have a member divided into two parts, two or more parts in the segments, into segments, one or more members. Means your structure will be failed by a breakage. Then after buckling, sliding, overturning, sinking, these are the failure types. Then here is a while we design a structure by limit state of collapse, we have some assumption here. Assumption like plane section normal to axis remain plane after bending. Plane section remain plane after bending. These are the assumptions. Okay, the tensile strength of concrete is ignored. We ignore tensile strength of concrete. Then the stresses in the reinforcement are derived from the respective stress strain curve for the type of steel used. Okay, means in this method we follow the actual stress strain curve of the steel. Okay, then the second topic is serviceability. In the limits of serviceability related to performance or a behavior of the structure at working loads and are based on the causing effective serviceability of the structure. Okay, in the collapse we get a safety, ensure a safety of the structure, but in the serviceability we ensure a performance. Okay, by this phenomena, by this two method I can say like this, in the limit state of collapse we don't get a performance of the structure. Performance means if you assume there is a load on your structure is a 40 kN per meter, but your structure will be collapsed at a 100 kilonewton per meter, 100 kilonewton, okay, but the working load is only 10. So we design a structure as a 100 kilonewton per meter, 100 kilonewton. So when we design a structure by a 100 kilonewton, your structure will be get a more material, its size will be bigger, economic cost will be higher, so it will not give the better performance. But a working load means your structure will only register 10 kilonewton load, 10 kilonewton load. So by the serviceability, we design a structure by a 10 kilonewton. So in this method, we can ensure performance of the structure. Okay. Now one more thing, there is a limit state of collapse is used for the design of the structure, while limit state of serviceability it's used for the check. For the check. If you design a structure by the collapsing load, you have to ensure safety. But by serviceability, we ensure performance. So both conditions will be fulfilled. So we design a structure by the limit state of collapse. But after a design completed, we ensure performance by serviceability because we have done some check. So these are the two types of check here: limit state of deflection, limit state of cracking, and other limit state. So we start a limit state of deflection and limit state of cracking. These are the two methods here: limit state of deflection and limit state of cracking. So limit state of deflection is designed to this limit state safeguard the serviceability of the structure from the adverse effect of excessive deflection. Excessive deflection. But in the cracking, designed to this limit state safeguard the serviceability of the structure against damage due to excessive cracking. So in the limit state of deflection, we control the effect of the deflection. In the cracking, we control the effect of cracking. So why we control the effect of deflection? Here is some condition here. Excessive deflection creates feeling the lack of safety. Same phenomenon here. Crack creates a feeling a lack of safety. Its effect geometry and shape enhance the appearance of the structure. Okay. It leads misaligned and sensitive and machinery. It leads the deformation of door and window frame. These are the deflection conditions here. If this structure will be deflect, this type of failure you can see. By the cracking, we have the appearance exposed surface. Exposed surface will be exposed by the cracking, then creating a leakage problem, then create a corrosion of steel because your steel will be opened by a crack. It will be reached by water. So by the water reaches the steel and your steel will be corroded. It creates the problem of poor drainage and ponding on roof. It reduces the stiffness of the member. It creates lots of maintenance problems. Lots of maintenance problems. These are the phenomena of limit state of deflection and limit state of cracking. So how we can control a deflection and control a cracking? So for the controller deflection, we have to follow IS 456 2000 page number 37 clause number 23.2.1. In this clause, we have a L by D ratio. L by D ratio. Length by effective depth ratio. L by D ratio. Okay. For the cracking, we have to follow IS 456 2000 page number 47. So for the control of cracking, we have to secure a reinforcement spacing. we have to secure reinforcement spacing. For the secure reinforcement spacing, for the beam, we have to follow table 15. For the slab, here, for the main reinforcement and distribution steel. This all value you can find in the IS code, IS 456 2000. Here is a complete limit state of deflection, diffident cracking, and second one is other limit state. In the other limit state, we have to control a vibration, fire resistance, and durability. So in the vibration, while your structure is subjected to dynamic load, at dynamic load, that time we have to ensure safety against vibration. When we design a structure for the resisting the flame, resisting to a flame penetration or heat transmission, that time we have to secure a structure for the fire resistance. Same formula here is durability. For the durability, we have to exposure condition. Exposure condition means in the rain or continuous underwater or sea water or freezing, thawing or aggressive chemicals. At that time we have to secure our structure. So in this condition we have to follow limit state of durability. Okay, this all three other limits you can understood. Here is the limit state method is completed. Here is a partial safety factor. First partial safety factor for the material. Why we use a partial safety factor? Because at the some time we have the inadequate compaction, inadequate curing, construction fault, impurities in material, bad weather, dirt or oil in reinforcement, corrosion of reinforcement, or improper mixing. This type of condition which reduce the material strength. Okay, so while we reduce the material strength, this material strength is reduced, we have to balance it. So for the balance we have to follow partial safety factor. This condition for the material and this condition for the load. Partial safety factor for the load, we have following reason here: error in load assessment, possible overloading, load combination, repeated loading, and modification in load. So by these errors are for the material and this error for the load. So this error you can be design a wrong structure. By this error your structure will not carry that much load that you design for it. Okay, so for this type of error we follow IS 456 page number 2000, page number 68. For the concrete we have partial safety factor 1.5 and for the steel 1.15. Understood? It's a simple partial safety factor here. For the concrete 1.5 and for the steel 1.15. Now we start a neutral axis. So what is a neutral axis? So neutral axis is like a separate compression zone and tension zone in a cross section. Of a beam. Okay, shall I draw a figure here? Here is your beam cross section, and this is your neutral axis NA. So your structure, neutral axis means your structure divided in compression and tension zone. So upper portion is compression and below portion is tension. It's tension. So this axis, this line, imaginary line, divide a compression zone and tension zone. We call this line as a neutral axis. Okay, neutral axis says okay, great. So by the above portion is compression and below portion is tension. So we have to find the depth of neutral axis. Depth means from top of the structure to the neutral axis depth. Here is the equation for the compressor, 0.36 FCKB into XU, and for the tension 0.87 FYAST. This both equation you have to remember, or I must say you write down in your notebook. These two equation is so important for the design of the structure and analysis of the structure. Okay, one more point is here. This compression force is carried by only concrete and tension force only by steel. These are the assumptions for the singly reinforced beam. This both compression and tension equation is both used for the only for the singly reinforced beam. For the doubly reinforced beam, we have a different equation. For the compression, okay, we will learn it in the next lectures. Okay, here is the where XU is equal to neutral axis depth, area of steel AST, B is the width of beam, FCK is equal to strength of concrete, Fy is equal to strength of steel. But we have a C is equal to T. This condition, therefore, when we apply this type of condition, C is equal to T. Assume is your beam here, your neutral axis pass from here. At this axis, your compression is 0 and tension always 0. Both are 0. Tension and compression both are 0 at the neutral axis. So if I say C is equal to T, its condition will be followed. Its condition will be safe here. Yeah. So same condition here, C is equal to T. 0.36 FCKB into XU is equal to 0.87 FYAST. So we have to find XU. So here is XU, 0.87 FYAST divided by 0.36 FCKB. So this equation is for the find depth of neutral axis. Okay, so this equation will be used. So next is a maximum depth of neutral axis. So what is the maximum depth? There is a depth of neutral axis up to which brittle failure of concrete can be avoided is known as maximum depth of neutral axis. Okay. Brittle failure can be avoided at the depth of the neutral axis. This is called a maximum depth of neutral axis. So what is brittle failure? Brittle failure is failure due to concrete, and failure due to steel is called ductile failure. Okay, for find XU max, we have to follow IS 456 2000, page number 70. At page number 70 we have this type of table, Fy Newton per mm square into XU max. For the 250 grade steel, we have the 0.53 D, 415 grade steel 0.48 D, and 500 for 0.46 D. Here D is effective depth. D is equal to effective depth of structure. Okay, here is a section types. So what is a section type? We divide a beam based on the depth of neutral axis. Divide a beam by a depth of neutral axis. So we have a three type of section. One is balance section, second one is under reinforced section, and third one is over reinforced section. Okay, so we understood, we are going to understand these three type of section. Look at here. Here is a balanced section, under reinforced section, over reinforced section. So what is balanced section? Balanced section is required steel is equal to provide steel. Means whichever steel is required for the structure and you provide that much steel, it's called balanced section. Okay. For the under reinforced section, required steel is higher, but you provide less. Okay. Therefore, the over reinforced section, required is less, but you provided steel is higher, more than required. This type of section is called over reinforced section. These are the three conditions for the balance, under and over reinforced section. Let's check all the condition here. Here, XU is equal to XU max for the balance section. XU less than XU max is under reinforced section. XU greater than XU max is over reinforced section. For the PT limit, PT is equal to PT limit. For the under reinforced, PT less than PT limit. For the over reinforced, PT greater than PT limit. Same condition for the MU. MU means moment, PT means percentage of steel. So MU is equal to MU limit for the balance section, MU less than MU limit for the under reinforced section, and MU greater than MU limit is over reinforced section. So here is, you can see here, PT limit is more, means PT limits means it's a required steel and PT is provided steel. Both are different. You understood here? Simple logic. Same thing for the moment limit. Moment limit means required limit and MU is provided limit. Provided moment. Okay? Understood both of them? For the under we have a less, for the over we have a greater. Simple logic, simple logic. You will understood very easily. Understood? Section type is completed. Here is a strain diagram for the balance section, under reinforced section, over reinforced section. You can see here is a neutral axis depth, XU max here, and XU is above for the under reinforced section. XU is below than XU max is called over reinforced section. Understood? Here is a stress diagram. Stress diagram you can see. Look at here. It's your graph. Your stress will be for the neutral axis only. Your compression force is looking at the point 42 XU and T at the bottom at the reinforcement level. You can find a tension. Here is a compression force, here is a tension force. Understood? So simple. So simple. Then we start an example. Example here for the find a neutral axis, and by the find a neutral axis depth we have to find out type of beam. Write down the example. A beam size 230 by 300 mm. Built with M20 grade cement and Fe 250 grade steel, and here is a provided 4 numbers of bar with 60 mm diameter. By this example we can draw a figure. By this example we can draw a figure. Figure of what? Figure of cross section of beam. Figure of cross section of beam. Look at here. Here is a beam dimension 230. Here is 300, and we have 4 numbers of bar at 60 mm diameter. Figure is completed. Look at here, given data. B is equal to 230 mm. D is equal to 300 mm. FCK 20 Newton per mm square. Fy 250 Newton per mm square. These are the given data. We starting a calculate here. I am assigning. Okay. We are going to jump on the Word file. Look at here. Same example here. We write down the given data. First of all, we have to find the AST, area of steel. Area of steel, you can see here. By the area of steel, we can find a 60 mm diameter. So 4 into pi by 4 into 60 whole square. Four into pi by 4 into 60 whole square. So you can see here the value is 804.24 mm square. So by the area of tension steel, we have to find a neutral axis depth. Here is the equation. XU is equal to 0.87 Fy AST 0.36 FCKB. Write down all the values which we have. Fy means of 250, AST area of steel we have find out, and FCK it's 20. Putting down all the value, we have find XU 105.62 mm. Then after we have the XU max. XU max equation we can find from the IS 456 page number 70. From the IS 456 we get XU max value here 0.533. 0.533 into 300. 300 is effective depth, which is given in the example, and calculate. We got the 159 mm. Here is XU less than XU max. XU less than XU max. This condition we say that the beam section is under reinforced. Beam section is under reinforced. First example finish. Second example. Here is a second example. We have a rectangular beam constructed with M20 grade cement and Fe 250 grade steel, and size of beam is 230 by 350 mm. Find the depth of neutral axis and type of beam. In a tension zone, 4 number of steel bar provided with 20 mm diameter. So let's create a one diagram, one cross section of a beam which given by the exam. Here we have a 230 width, 350 depth, and 4 numbers of bar of 20 mm diameter. Okay, this is the cross section of the beam. Here is the given data. FCK 20 Newton per mm square, Fy 250 Newton per mm square, B is equal to 230 mm, width and depth 350 mm. These are the given data in the example. So let's calculate. Okay, this is the example here. First of all is given data, we all discuss it. Then here AST, area of steel, is 4 into pi by 4 into 20 whole square, because we have a 20 mm diameter of bar. Okay, so by the calculator we have find the area 1256.65 mm square, and then after we have to find XU is equal to 0.67 Fy AST upon 0.36 FCK B. So give a value, assign a value 0.87 Fy 250 AST 1256.63, 0.36 FCK 20 B 230. So here is a XU 165.04 mm. Then after XU max, I told you have to find XU max equation from IS 456 page number 70. Assign a D. D means effective depth, which is 300. So 0.53 into D100, we have to value 159 mm. So here is a XU is greater than XU max. So by this condition, we conclude that there is our reinforcement is over reinforced section. Reinforcement is over reinforced section. Understood? So here's our second unit is complete.